Today, on how it's made. Automotive fuel pumps. Without them, we'd be running on empty. Cricket bats. It don't mean a thing if it ain't got that swing. Change machines. Ka-ching, ka-ching, to coin a phrase. And ductile iron pipe. How it's made goes underground. When you start your car, it activates a pump that's usually located inside the gas tank. This electrical pump pushes the gas out of the tank to injectors, which aerate the gas and deliver it to the engine's cylinders. Without a pump to get fuel flowing, you'd be going nowhere. You might think that submerging an electrical pump in gasoline would be a risky thing. But because liquid fuel doesn't explode on its own, it's actually a very safe place to put it. They begin with the pumping mechanism, sandwiching a gear and several rollers between two metal plates. The rollers will rotate to pull fuel into the pump and then push it out. They test each roller assembly by spinning it from the bottom. A robot then pops it out and moves it to the next station. Here they attach the electrical motor to the roller pumping mechanism. Then they slide a magnetic sleeve over the assembly and cap it. All the parts that make up the pumping mechanism have now been assembled. Next, they install an end cap that includes a filter made of metal mesh. They slide a metal sleeve over the pump unit and press fit it together. Inside this special chamber, large magnets generate a very strong magnetic field. The magnetic force field actually causes the metal sleeve to collapse. This crimps the sleeve at one end, holding everything together. Next, they place retainer rings into slots in the fuel pump cap. They place a metal bracket over the pump. The bracket steadies it and serves as a guide as they install the brushes and coils, which will supply electricity to the fuel pump motor. They slide a brass terminal onto the end of each coil and brush assembly to facilitate the electrical connection. Then they press fit the terminals to the assembly so they're firmly attached. When the job is done, a robot removes the bracket. They've built this fuel pump from the inside out, and now the actual workings are complete. They hook each pump up to a power source and run fluid through it to test the pumping action. Then they check for proper flow and pressure. If the pump passes inspection, a robot sends it down the assembly line, where they assemble the system of tubing that will carry the gasoline to the engine. They seal the joints with a brazing paste. Then it's into a gas oven that bakes the brazing paste, causing it to harden and fuse to the tubing. Using oven mitts, they remove the tubing from the oven and brush off any unwanted bits of metal and hardened paste. They cap the tubing to keep dirt and debris out as a packaging precaution. Now they hook up some rubber tubing to the pump and secure it with metal clamps. They link it to the rest of the piping and hoses. They wire the fuel pump and hook up a connector to attach it to the engine's wiring. This is the sending unit, It's a float with a metal arm that's attached to an electronic sensor. The sensor sends information about fuel levels to the fuel gauge on the car dashboard. They use a computerized system to check the sending unit's accuracy as they move it up and down. This pump is ready to handle the highs and lows of the gas tank, and it's time to hit the road. References to the game of cricket date back to the 1300s. Historians believe it started as a children's game. In the 1600s, working men began taking up the game as a pastime, and before long it caught on with the upper classes. By the 18th century, cricket was a major organized sport in England. Cricket bats are made of a particular species of white willow. It has stringy wood fibers that are unusually long. These give the wood elasticity, the key to its performance. Bat makers use as much sapwood as possible. It's moister than the heartwood at the tree's core because sap runs through it. Production begins with willow pieces 3/4 of a meter long. The first machine trims them down roughly to size. A few sprays of water limber up the wood fibers. Then each piece goes through a pressing machine 3 to 4 times. A curved roller applies up to 3 tons of pressure, rounding the bat's face and compressing the wood by up to a centimeter. This pressing is essential because it determines the bat's performance and durability. The bat maker draws a V on the end where the bat handle will attach. Then he removes the bulk of the wood behind the V on a table saw. This minimizes the amount of work he'll have to do later by hand. Now he cuts out the V. This creates a joint in which to insert the handle. The handle is made of cane, dried vine stems, glued together in sections and coated with rubber. The end the player grips has been shaped on a lathe. The other end will attach to the blade. The bat maker cuts the block-shaped tip into a wedge that'll fit into the V-cut, then glues the 2 pieces together. A few taps with a hammer ensure a tight fit. He spreads the glue that oozes out all over the joint to seal it. Now he shapes the profile, using a classic woodworking tool called a draw knife. This takes only a few minutes, but requires years of experience and an expert eye. Then he completes the shaping with another pressing to curve the bottom third of the bat. International cricket rules regulate the length and width of bats, but there's no restriction on curve. Getting this right is tricky though. Too much curve, and he'll harden the blade, losing performance. The bat maker finishes off the shape using specialized craft tools. Then he uses a metal hand plane to flatten the blade's edges. He ensures the bat has good spring by hitting it with a dense wooden mallet. He also analyzes the sound of the strike. The softer the sound, the softer the wood, and the better the bat will play. He smooths the bat against a drum sander. The air-filled drum molds to the bat, so it doesn't wear away the shape he worked so hard to achieve. Then a worker smooths out the rest with a belt sander, custom made for the bat's shape. On each machine, they sand the entire bat twice, first with a coarse abrasive, then with a fine one. Next, they mount the bat on a binding machine and coat the handle with glue. Twine wrapping binds together the rubber-coated cane sections that make up the handle. They apply extra glue to prevent the twine from unraveling. Next, they polish the blade against a cotton wheel. Once the wood is shiny enough, they stick on decals with the bat's brand name. Then slip on a rubber grip over the binding to prevent the player's hands from slipping. The bat's two main materials complement each other when striking the ball. The willow wood blade flexes enough to deliver a good hit. The cane handle absorbs that energy, protecting the player's hands. Change machines were invented in the mid-1950s. Vending machines were becoming more popular, driving a need for change. They began as simple mechanical coin changers, converting a quarter into nickels and dimes. Today's modern machines can even convert $20 bills. Times sure have changed. It's like magic. In goes the bill, and presto, out comes the exact change. But there's no sleight of hand, just innovative design and some pretty high-tech equipment. Production begins with the machine's cabinet. A computer-guided laser cuts the cabinet parts from a sheet of steel measuring 1 by 1.5 meters. Workers shake the parts free and push out the openings in the panel that will become the cabinet's front door. They shape the parts in a machine called a press brake. This is one of the door panels. The machine forces it against a die, bending the edge. These bent edges will strengthen the door and help it fit snugly into the frame. The laser cutter also makes a series of holes in another cabinet part. Then workers press threaded studs into the holes. A vibrating feeder dispenses the studs into the insertion machine they use. Now they bend the sheet, again using a press brake, and make the three-sided panel that will become the cabinet sides and back. To that, they attach the top and bottom panels. Then they set it in position on a computerized welding station and rotate the table. A robot makes precision welds behind a steel partition that shields the worker from heat and harmful rays. Now they assemble the change machine's coin dispenser. It has two counter-rotating discs fitted to the diameter and thickness of a coin. They work together to seize and align the coins, then drop the change into the coin chute. Workers set in these metal discs and a plastic gear mechanism that rotates them. Then they secure the parts on a fixture and drill holes into the gear mechanism. Next, they insert roll pins to hold the parts together. The coin discs, if properly assembled, will spin freely. Now workers can assemble the coin dispenser discs and gears. This is precision work. First, they set parts in a metal casing. Plastic rings go around the discs to guide and support the gears. Then they attach the gear train motor that powers the discs that dispense the correct change. A plastic guide on the casing helps the coins drop in properly. Next comes a coin chute that guides the change out of the dispenser into the machine's coin cup. The dispenser holds up to $800, which can weigh a hefty 20 kilos, so they add a handle, which locks in with this tool called a ring fastener. Now it's time to put it all together. First, they install the electric power supply on the inside back wall. Next comes the bill validator. and the coin cup. Then the coin dispenser and electronic control board, the brains of the machine that calculates the change. Finally, on go the instruction decals. So, how does it all work? Let's open the door and see. First, the bill acceptor scans the bill's paper and ink and stacks it in a box. Then, ka-ching, out comes the exact change. Chances are you use ductile iron pipe every day and don't even know it. The underground pipes that bring your drinking water are cast from ductile iron. So are the sewer pipes that take away household waste. Ductile iron is more flexible than ordinary gray iron. Under pressure, a ductile iron pipe will bend before it will break. Ductile iron pipes are made of 90% recycled metal and have a lifespan of hundreds of years. Production begins in the pipe factory's scrapyard. These old cars are on their way to a shredder that chews them up into little bits. The factory sorts the bits by material. It discards the plastic, sells the aluminum and copper, but keeps the steel and iron. The factory also gets scrap steel from demolished buildings and other sources. After analyzing the chemical composition, it sorts the shredded metal accordingly. The crane operator uses an industrial magnet to gather a specific weight of each type of steel and iron. The shredded metals go into a blast furnace fueled by coke, a form of coal. At 1400 degrees Celsius, the iron and steel liquefy, while impurities are carried away. Workers then add magnesium. This turns the metal from ordinary gray iron into stronger, more flexible, ductile iron. The molten iron travels down a trough into a casting machine. It enters a spinning mold. Centrifugal force spreads the iron against the mold walls. A cooling system chills the walls, so the iron solidifies within seconds. Then an extractor pulls out a 6-meter cast iron pipe, the standard industry length. Before each casting, workers insert a round form, called a core, into one end of the pipe mold. Iron fills the void between the core and mold, forming a flared edge, called a bell. The core also seals off that end of the mold, preventing molten iron from flying out during casting. To connect pipes, installers fit the bell of one pipe over the straight end of the next one. A rubber gasket seals the link together. They can make pipes of different diameters with the same casting machine by changing the size of the mold inside. After extracting the pipe, the factory weighs it and measures the wall thickness to ensure everything meets specifications. Then, on the bell end, they remove the core. It's made of sand and plastic resin, so it simply disintegrates. This factory makes pipes in several diameters. But regardless of size, the casting process is always the same. It just takes less time with smaller pipes because they solidify faster. A freshly cast pipe is about 800 degrees Celsius, but as soon as it leaves the mold, it cools quickly. Such rapid cooling makes the iron brittle, so the pipe goes directly into a gas-fired annealing furnace that reheats it to 930 degrees Celsius. This alters the internal structure of the iron, making it flexible again. The pipe then runs through a cooling chamber that showers it in cold water. To prevent the iron from corroding, they spray the inside with cement, building up a lining 3 millimeters thick. Then they smooth it out by spinning the pipe for a few seconds. They paint the entire pipe, inside and out. That seals the surface, enabling the cement to cure over the next 24 hours. It also provides some extra rust protection. Finally, a robot paints a stripe around the straight end of each pipe. This is a depth guideline to let the installation crews know when they've inserted the straight end of one pipe as far as it can go into the bell end of the next one.